Right, so now for lecture 2 part B. Now at the end of this lecture you will also understand second and zero order reactions. And for second order reactions and first order reactions, you'll be able to draw graphs from data of concentration versus time. You'll be able to calculate the rate constants for a first, a second, and a zero order reaction. You'll be able to define second order reactions and differentiate between homomolecular and heteromolecular cases. And you'll be able to define and provide an example of pseudo first order reactions. Many reaction steps involve collisions, and second order reactions are more complex because of this. So this would be collisions between two molecules, meaning that the reaction is second order. It has one of the steps, the step that determines the rate of the reaction, will involve two molecules that collide. Now there are two types of second order reaction that you can think about. First is where the two molecules that collide to react are both the same, so that's a homomolecular case. And the second is a rate law where it's second order because it's first order respect to one reactant and first order with respect to another reactant, so second order overall. And that's two different species that are interacting with each other here, and that's the heteromolecular case. So we're going to begin by talking about the homomolecular case because that is an example where we have some very simple maths that we can also use to help us think more about the second order reaction. So in this case, the rate law is that the rate equals K, the rate constant, times the concentration of the reactant squared. Now, as you measure the reactant concentration, it will decrease with time, but not in the same rate or in the same way as a first order reaction. And we know that for a first order reaction, if you log the concentration of the reactant and plot that against time, you'll get a straight line. But for a second order reaction, you would not get a straight line. You would get a curved line if you logged the concentration and plotted it against time. And that's because this is not first order kinetics. In the homomolecular second order reaction case, we have two molecules of A reacting with each other to form products. The rate law is the rate equals K times the concentration of A squared. If we measure the concentration of A and see how it changes with time, we get minus dA by dt, so the rate of consumption of A, and that is our rate, and that equals K times the concentration of A squared. We know that because this is a second order reaction. And this gives us an equation that we can integrate. You do not need to be able to integrate, but there is a step that will go from that top equation in pink to the equation underneath, which is called integration, and that between two limits. And that gives us this equation here called the integrated second order rate law. That is 1 over A2 equals KT plus 1 over A naught. And this equation is only for the homomolecular case, because the only example where we can simplify the equation in such a way to be able to integrate it like this. And this is useful because we have now an equation that is in the form of y equals mx plus c. And that means that if we take y as 1 over our measured concentration of reactant, so 1 over AT, and we take x to be t, the time, then if we plot 1 over the concentration against time, we will get a straight line. And in this case, the gradient will equal the rate constant. So for a homomolecular second order reaction, a plot of 1 over concentration against time will give you a straight line. Whereas for a first order reaction, a plot of the natural log of concentration against time will give you a straight line. If this is a second order reaction, you would then know from doing these two plots. The log plot won't work, but the 1 over concentration of A will give you a straight line. And you can see it has a positive gradient because the gradient equals the rate constant. So when we were talking about first order reactions, there was a case where we could look at the half-life, so the time it takes for the concentration to halve, and that gave us a constant value, showing that the half-life is constant, and as you know, that means that we had a case where we had a decay that was exponential. But that's not the case for a second order integrated rate equation. If you take this equation and you say that at the half-life, where t equals t to the t half, just meaning half-life, then the concentration will equal half the initial concentration. And if you put that into this equation, it will simplify to the half-life, which is t to the half, equaling 1 over k times the initial concentration. So you can see here that you can calculate the half-life, but it does depend on the starting concentration now. It is not, so it would be constant for a particular reaction, but only at the start of the reaction. It depends on the starting concentration of the reaction. It is not independent of concentration. So, first of all, if you have a set of data of concentration of a reactant against time, and we would see the concentration of reactant decaying over time, as you can see in this plot. Is that a second order, homomolecular second order reaction, or a first order reaction? It might be neither, but we could determine if it is one of these by doing a simple thing. Could plot the equation in the log form. It's a log of concentration over time. If it gives us a straight line, then it is first order. Or we can plot 1 over concentration against time, and if that gives us a straight line, then it is a second order reaction of the type of homomolecular second order. So second order reactions can be homomolecular in that case where you have rate equal to the concentration, rate equal to the rate constant times the concentration of reactant squared, but it can also be heteromolecular. So rate would equal K times the concentration of one of the reactants times the concentration of another reactant. And that, we wouldn't be able to simplify that using an integrated method to give us the integrated rate equation that you saw before. So it's a little bit harder to consider that using the types of maths that we have already discussed. So what would you do? In the case of a heteromolecular second order reaction, where we have the concentration of A plus the concentration of B going on to form products, we will have that the rate equals K, A times B. Doesn't matter what the stoichiometry of the overall reaction is. If this is a second order reaction, then it will be A to the power of 1 and B to the power of 1 to be second order overall. And there are two extreme cases for a second order reaction that will simplify things for us. First of all is if we know that the concentration of the two reactants is the same. So if we start with equal concentrations of both of our reactants, So we know that they equal, and they will continue to equal throughout the reaction because they're both decaying maybe at the same rate. If we know that, then the kinetics will become the same as the homomolecular case. And the other extreme case that we can have is if we know that the concentration of one of the reactants is very much higher than the concentration of the other reactant at the beginning of our reaction, then we can assume the reaction is something called pseudo first order, and so simplify our kinetics using first order kinetic equations. So I'll show you those two extreme cases. So extreme case 1 be the concentration of A and B are equal, a second order reaction where A plus B goes on to form AB, and the rate is equal to K times the concentration of A times the concentration of B. If the stoichiometry therefore is 1-to-1 in that reaction, and the rate law is also first order for both A and B, in that case, we know that the concentration of A and the concentration of B will be equal at all times if we start with the same concentration for both. And in that case, we can simplify our rate to rate equals concentration of A squared. And it becomes the same as the homomolecular case. In extreme case 2, in this case, the concentration of B, or one of your reactants, will be much, much greater than the concentration of the other. So think about this where you have a drug that is decomposing in water. Now you might think, well, water actually in that case does have a concentration. There is a number of molecules of water per litre. And actually the concentration of water as water is 56 molar. And if the concentration of the drug in the water was 0.01 molar, then you could agree that there's significantly more water. And in fact, as the drug decomposes in water, even if water molecules aid that decomposition process, we will always have a significant amount of water. Okay, so in a case like this, if all the drug reacts, the concentration of water really doesn't change. It stays as 56 molar. So the reaction will behave as a first order reaction. So even though the decomposition of the drug in water does involve the water molecules, they are a reactant in the process, we can see that in fact the concentration of water doesn't play a role in the rate of the reaction. So pseudo means fake. It is a fake first order reaction. So in a case where the concentration of one of the reactants is very much greater than the concentration of the other, what happens to the maths? So the rate, as we know, equals K times the concentration of A times the concentration of B. B is in great excess. So that means that throughout the reaction, it looks like the concentration of B doesn't change, because compared to the concentration of A, it appears not to change. So it appears to be constant. And in that case, the rate simplifies so that the variables are no longer both the concentration of A and the concentration of B. It's now just the concentration of A. And this means the constant in that rate law is K times B. Okay, and this has simplified it, and what we have there is a rate law. So our rate, which as you know is minus dA by dt, that's what we're going to measure, equals K, and this time we have a dash, K prime We call that dash prime. So K prime times the concentration of A, which is first order. But K prime equals the true rate constant times the initial concentration of B. Because B is in great excess, that concentration really doesn't change over time. It maybe changes by, what, 0.001% of its initial amount, but it looks like it doesn't change. A good example would be, think about a reactant where you have 100 times more of one of the reactants than the other. When one of the reactants is completely used up, there will still be 99% of the other reactant still remaining. So throughout the entire reaction, we've gone from 100% to 99%, which you could argue is pretty much constant. And that is how first order kinetics, pseudo first order kinetics works. It's by having one of the reactants in great excess. The example that I have given you about our drug being A with a concentration of 0.01 molar in water, which is B, and water has a concentration of 56 molar. It's hard to think of water as a solvent having a concentration, but it does. It has a number of moles in a litre. Okay. We know just intuitively that the water in our reaction here is going to remain the same throughout. And so we know that as all of that reactant, all of that drug decomposes, the amount of water is pretty much going to stay the same. So we have pseudo first order kinetics. So just to go through that with the graphs here, you can see that if B is in great excess, so very much more of the concentration of B in our system, as all of the one reactant is used up, the amount of the other reactant is used is so small you can't see any change. And in that case, then the reaction looks like it is first order. It is fake first order. And there are a huge number of reactions that follow this sort of kinetics. So if you're defining pseudo first order, remember the term fake first order, and remember this example of drug in water, where the concentration of drug will react and disappear, and the concentration of water doesn't change, even though water is one of the reactants. Or another example is a reaction that involves oxygen that is in the air. We know that if you remove oxygen from the air, it will immediately be replenished by more oxygen. So even if oxygen is one of the reactants, its concentration will not change. It will continue to be replenished. So any reaction that involves oxygen from the atmosphere is going to appear again as a first order reaction if it only has one other reactant. Okay. So those are two simple examples that you can think about when trying to explain first order, pseudo first order kinetics as an extreme case of a second order reaction. This is a bit of an aside. Bayer discovered the process of acetylation reaction, and it provided us with heroin and aspirin using the same reaction. One had the acetylation from morphine, and the second had the acetylation from salicylic acid. So that acetylation process that Bayer discovered enabled them to produce two very famous drugs, aspirin and heroin. Now, aspirin in my childhood was marketed for children and was available as a dispersible tablet and never as a liquid formulation. Paracetamol is now available as a suspension, but aspirin isn't. Why? Well, this is because the ester bonds within aspirin are very susceptible to hydrolysis. The reaction of water with the ester bonds will make it go back to salicylic acid, and this could cause gastric bleeding. So a jar of old tablets of aspirin might smell of vinegar, because as well as salicylic acid, they will have also formed acetic acid. So we can see here if that reaction is going backwards as it begins to hydrolyze. So we have our aspirin, and if it is in the environment for too long, it will go back to form salicylic acid and acetic acid. And if we look at the rate of change of aspirin over time, you can see that if you plot the natural log of concentration of salicylic acid, the aspirin against time, you'll get a straight line, because this appears to follow first order kinetics. And there are a number of natural processes that do this. It is using water from the air, or it could, if you have dissolved the aspirin in water, it could be using it from that solution. But even if you have water in even if you have your aspirin in a tablet, it will be interacting with water from the air. Now, as you know, the water from the air is continually replaced, and so the concentration of water in the air is not changing, it is staying constant. And so the reaction has pseudo first order kinetics. And this means we can work out the half-life of aspirin in air, or the half-life of aspirin in water, by using the fact that the half-life equals the log of 2 over the rate constant. And in our pseudo first order reaction here, the rate constant is made up of the true rate constant, because it's the pseudo rate constant that we have measured here. So it's made up of the true rate constant plus the concentration of the other reactant, which will either be the concentration of water that's in air, or if you're measuring the rate of reaction in solution, it would be the concentration of water in the solution. One final example I would like to mention to you now, that you will hear this term in pharmaceutics lectures, is the term zero order reactions. And you'll hear this, as I said, when looking at controlled release of a drug from a particular formulation in pharmaceutics, and when considering the role of an enzyme in a reaction. This is where the rate does not depend on the concentration of the reactants. So in this case, a graph of concentration of the reactant against time will be a straight line. The rate, which is the gradient, doesn't change with concentration, and so is independent of concentration. A catalyst is not a reactant, it doesn't get used up in a reaction, so you can have a reaction where the rate does not depend on the reactant. The release of drug from a controlled release formulation often does not depend on the concentration of drug in the formulation, but rather it depends on the controlled delivery device itself. So again, it is zero order with respect to the reactant. with respect to the drug that is being released. So there are examples, many examples, where you might see a case where you're seeing zero order kinetics. And in that case, you will see a straight line by plotting concentration of A against time. So in summary of lecture 2, we have introduced to you, as well as a lot of concepts, an awful lot of equations as well. Now, I want to note, and there is some information on Blackboard about this, that if I refer to an equation in an exam, I will provide it. I don't want you to memorize equations, but I do need you to be able to use them. You will need to be able to remember what a first and a second order rate law is, and the type of graph needed to plot a first or second order reaction, to see that it's a first or second order reaction, and to calculate K. And you should also know that the half-life first order reaction is 0.693 over K, and thus not dependent on the initial concentration. Whereas the half-life for a second order reaction, you don't need to know what that is. You just need to know that it is not independent of concentration of the reactant. It does depend on reactant concentration. So I want you to focus on the concepts rather than focusing on memorizing the equations. But you do need to know how to use the equations, when to use the equations. And there's more information on that that you can find on Blackboard.